Welcome to the afternoon lectures in this second day of the UFSCar Workshop on PDEs 2022 online edition. We will have two lectures by Professors Eduardo Teixeira and João Marcos Duó. Let me recall that if you have any questions or remarks, please write it down in the comments place on YouTube. You should log in to do it. We invite you to share your comments or questions with the speaker and the audience. Our first speaker in this afternoon session is Professor Eduardo Teixeira, which is full professor from University of Central Florida, USA. His research interests include free boundary problems and regularity theory for nonlinear partial differential equations. Among the distinctions Professor Teixeira received, we can mention the Mathematical Congress of the Americas Prize and the ICTP-IMU Ramanujan Prize. Professor Eduardo Teixeira, welcome to our workshop. It is a great pleasure for us to have you on the workshop.
Excellent. Okay, thank you so much, Gustavo. It's always a delight to be introduced by a good friend of ours. So thank you so much. It's a great pleasure and an honor for me to take part once again of this very interesting, very nice workshop organized by Universidade Federal de São Carlos. It's even if it's in an online environment, it's nice to be back in São Carlos. I spent a year there in 2015, and then I got the opportunity to meet all of you in person and strengthen even more my connection with the universities in São Carlos. Okay,
thank you, Professor.
My pleasure. So yeah, so today what I'd like to discuss is this kind of a program that we have been developing in several years, which has to do with this idea of a non-physical free boundaries. And I will explain what I mean by that. And hopefully towards the end, I'll show some new results that one can obtain by applying these kind of ideas and technologies to some specific problems. Okay, so for the sake of motivation, let me start by revisiting a very important, beautiful mathematical physics problem called the obstacle problem. And the way to place, there are many interpretations of this problem, but one way that I like to think about this problem is the following: is to find the equilibrium position of a membrane resting above a given obstacle. Okay, if I don't have an obstacle, basically I have the Laplace equation or the minimal surface theory. But if I have an obstacle, the picture that I want you guys to keep in mind is this one. Okay, so the membrane is going to adjust itself as to with the geometry of the obstacle problem, and it's a very beautiful problem because it's very simple to state. It's very similar to a very well-known problem like the Dirichlet integral, but just because you introduced an obstacle, there is a major difference between the harmonic functions and the obstacle, and this major difference is what I'd like to explore today with you. So this is the obstacle problem. One way to interpret this is by minimizing the Dirichlet integral. And the only difference is that, I mean, you prescribe some boundary conditions, which I'm not saying here, but the main difference is that I can only allow candidates, in other words, functions that are above this given obstacle. And the key picture is that this function is going to be harmonic in the non-constant set. Whenever u is above the obstacle, then you can perturb up and down, and then solutions. This solution is harmonic, and the key property is that solutions are just C11. Okay, so you see that because you have introduced an obstacle, regardless of the smoothness of the obstacle, you have a tremendous drop on regularity of solutions from real analyticity to C11. And that's what I'd like to explore today. But before I do so, let me show you the other part of the theory, the p-laplacian. Okay, apparently they're not connected, but the p-laplacian can be thought as the minimizers of the p-Dirichlet integral, and I'm going to put a forcing term just for the sake of illustration. And the minimizers do solve these very well-known elliptic operator. Okay, so this is very well known, and the key feature of this operator, of course, this operator is nonlinear, but the key feature is not the nonlinearity per se. The key feature is that the coefficients, I can think of the gradient of u to the power p minus 2 as the coefficient of the diffusion process, and these coefficients degenerate at critical points. Okay? So the known facts about this, the soft analysis, and what I mean by soft analysis, like the functional analysis aspect of the theory. Soft here by no means means easy. They are very, very hard problems, but it's just a way of classifying the kind of results that one get. So the soft analysis is very similar to the linear theory, but in the following sense: whenever you have existence and uniqueness, you should expect to have, in similar situation, the same kind of results. But again, they are much more involved, it's a much more complex theory. And because of that, these kind of results give rise to a very robust nonlinear potential theory that has been developing from late 60s all the way up to today. It's still a very active line of research to be able to prove these results for the p-laplacian. Okay, and the other feature is that even if you take f to be 0, so p-harmonic functions, they are just C1 alpha. Okay, and this is the key property that I'd like to explore with you today, is that solutions are just C1 alpha. And this is one of the main reasons why problems governed by the p-laplacian are much more involved from the mathematical point of view. Okay, so the analogy that I'm trying to pursue here is the following: there is a diffusion defect on the p-laplacian. So if you think of the linear operator, the uniform elliptic operator, Laplacian of u equals 0, solutions are real analytic. But the p-harmonic functions are just C1 alpha. So there is a regularity lost when you go from p equals 2 to p greater than 2. Okay, but, and this is the key point that I want to make, but if I just tell you that p-harmonic functions are just C1 alpha, I'm not telling the whole story. As a matter of fact, p-harmonic functions are real analytic, but they only fail to be C2 at critical points. Okay, so in fact, if I just say that p-harmonic functions are C1 alpha, I'm just giving you half of the information. Okay, and the analogy that I'm trying to, the key observation is this one: p-harmonic functions lose regularity at the critical points as much as solutions to the obstacle problem lose regularity along the free boundary. Okay, so to be more precise, if I just remove the critical points from the p-harmonic function, they're real analytic as much as solutions to the obstacle problem are real analytic away from the free boundary. Okay, so this immediately gives us an analogy that this is the analogy that I'm going to try to pursue today. Is that p-harmonic functions, they lose regularity at the critical points as much as solutions to the free boundary problems do along their corresponding free boundaries. Okay, but the point is that for free boundary problems, this is often a manifestation of a rather precise geometric behavior of the solution, which is prescribed directly or indirectly at the free boundary. That's what in free boundary theory we call free boundary condition. Okay, so if I prescribe it, it's a free boundary condition. Sometimes it's an indirect condition that comes from the very nature of the problem. Okay, but this is the analogy that I'm trying to convey. This is where this idea of non-physical free boundaries come from. Is the idea that maybe there are many problems where you see things happening that you should interpret those problems as if they were free boundary problems, even though you don't have like a physical free boundary, but you should perceive them as if they were. Okay, so the analogy goes as follows. So a smoothing defect in a given model, if you have a diffusion model, of course, indicates that the diffusion is fading. It's getting weaker and weaker. Okay, so that's the first analogy. For robust models, and robust here comes in quote marks. I will try to explain later what I mean by robust. Diffusion, when it happens intelligently, in the sense that if you are forcing in a model for a diffusion to be neglectable at a point, that's one thing. But for robust models, you expect that this is you don't restrict the function to be or the system to stop diffusing at a particular point. You say, okay, let it happen, and you let the intelligence of the diffusion system to decide where the system is going to stop diffusing. Okay, so in that sense, they should be treated as what I'm calling abstract or empiric or non-physical free boundary equations. Okay, and in the case of the p-laplacian, it's a very, I hope, if I did my job right, I hope by now it seems clear to my audience that critical points for p-harmonic functions should be thought as free boundary points, because you see, you're not imposing a function to have a critical point at a specific point. The critical points happen because it happens, but it happens in some intelligent way. And as a matter of fact, that's why you can estimate the Hausdorff dimension of such points. And the critical points are precisely where very important features of the model are dictated. Okay, so that's the analogy, and now I'm going to try to explain what you can do with such an analogy. Okay, so basically what I'm trying to say is that if you take like a p-harmonic function, the function is going to be real analytic everywhere, but locally it's just C1 alpha, and this C1 alpha happens precisely at the critical point. And if you want to understand like quantitative properties of the system, you should look at the critical points, okay, and try to understand how fast the function moves towards critical points. And this is going to tell me what's the regularity, the precise regularity that I can obtain by the p-laplacian diffusion system. Okay, and as a matter of fact, there is a major open question in the field of elliptic PDEs, is to find explicit lower bounds for the maximal C1 alpha regularity for p-harmonic functions. So solutions are C1 alpha. I know it is an alpha. I know that this alpha depends on dimension and on p, that we know, but there is no information, quantitative information whatsoever on how big this alpha is. Okay, and this is a major problem in the theory. And what I'm trying to say here is that if you want to address this problem, okay, so let me so there are no results in the plane, but the estimates are not universal. And what I'm trying to say here is that if you want to understand this problem, it is it is interesting to look this as if it were a free boundary problem. That's because I was saying, if you want to understand the C1 alpha estimates at critical points, this is precisely the same problem as understanding how fast U moves away from a critical point. Okay, if I have a critical point and I know that the solution, let's say, grows at most in a C1 1/3 fashion, that's precisely saying that the solution is C1 1/3 at that point. And because this is the only points where I lose regularity, I can put together a proof on that specific C1 alpha estimate for p-harmonic functions. Okay, and this is an important problem, and it is connected to a number of very deep problems, in particular differentiability of the best Lipschitz extension problem. So if you take like a Lipschitz boundary data and you try to extend it in the best Lipschitz way possible, the question asks whether this extension is going to be a differentiable function. Okay, so differentiability is already known, but we don't know C1, for instance, because I would like to know that I can do that in a universal fashion. So solutions would be C1. Making conjectures is free, right? So anyone can make any conjecture. Whether the conjecture is going to hold true or not, that's a different story. So my conjecture is that if you want to obtain C1 alpha explicit estimates for p-harmonic functions, the key point is 1/3. So my conjecture is that this best alpha is greater than or equal to 1/3 plus a small error that goes to 0 as p goes to infinity. Okay. Quite unfortunately, I don't have a proof for this conjecture yet, but there is another very important conjecture that I can tell you a little bit more about, and this is the following trade. If you're trying to understand optimal C1 alpha estimates for p-harmonic functions, this is a very complicated problem, extremely complicated problem. So one thing that you can try to do is to enlarge the class of solutions by saying that, okay, I don't want to restrict the theory for functions whose p-laplacian is 0, but I'm okay with the p-laplacian being a bounded function. So I have enlarged the class, the family of functions that I'm considering. And now I can make, at least in this case, I can make a more educated guess. And the guess is that this has to do with this CP prime regularity conjecture that says that solutions to that kind of PDE are CP prime, where P prime is precisely the conjugate exponent of P. Okay, so this is the conjecture. And we have a radially symmetric example where the P, which is x to the power P prime, is precisely P prime smooth at 0, right? So this gives rise to the conjecture. Okay. There are reasons for skepticism, even though I would like to think that the CP prime conjecture holds true, but there are reasons for skepticism. The first one is that the conjecture fails when p equals 2. In the uniform elliptic linear case, the conjecture is not true. This is saying that if you have a function whose Laplacian is bounded, this doesn't imply that solutions are C2, not even C11, right? So this is one of the issues. Of course, in this case, you are requesting too much. And you know, in regularity theory, whenever you have a integer regularity, is always a troublemaker, right? Lipschitz regularity and versus C1 regularity, C11 regularity versus C2 regularity. Those kind of regularities, they are always borderline cases, and they are slightly more sophisticated. The second reason for skepticism is that, if true, what I'm saying is that this very naive looking function, the absolute value of x to the power p prime, is the worst possible function among all functions whose p-Laplacian is bounded. Okay, This is a very naive looking radially symmetric function. So I don't know if this would be reasonable to expect. But the third, and for me, the most profound reason for skepticism is that if true, then what I'm saying is that because this is the radially symmetric function is one whose p-laplacian is actually constant, what I'm telling you is that if you have a non-homogeneous problem governed by the p-laplacian, then having the Laplacian of u being a real analytic function or being just bounded gives you the same regularity theory. Okay, so basically, if you add a non-homogeneous term, regardless if this non-homogeneous term, this forcing term, is a constant function or a real analytic function or just bounded with many jumps, I would still have the same regularity, the regularity theory. Okay, and this we know by Schauder theory or Poisson equation. This is very far from being true when the problem is governed by the Laplacian, like when p equals 2. Okay, there is just one reason to keep pursuing this kind of problems, that in fact the conjecture is 2 in the plane, and this is a result that we proved with a former student of mine, Damião Araújo, who's now a professor na Paraíba, and my friend José Miguel Urbano from Coimbra. Okay, so now what I'd like to discuss today is the next big question. Okay, so basically what I'm trying to understand is the following. If you assume, forget about the CP prime regularity conjecture, it's a very hard problem, but if you assume that the CP prime regularity conjecture can be proved, is there any regularity left? Okay, so that's the question I'm trying to answer. Okay, and for that I will consider non-homogeneous problems that also depend on the gradient. And what will be interesting to understand is when the forcing term vanishes at critical points as well. So it's basically you're going to have a zero compensated by zero in some abstract algebraic sense. Okay, so to fully understand the picture, and it took us quite some time to have these analogies well worked out, you have to go back to Caprali's dichotomy. This is a major result in the theory of pre-boundary problems, more specifically obstacle type problems. And the analogy that I'm trying to convey here can be explained in the following way. Caprali proved in his paper from 1977 that the critical point, the pre-boundary points in the obstacle problem can be understood can be classified in 2 different ways. There are the regular pre-boundary points. Basically, this is his definition. He says that a point is regular if this blow up converges. As a matter of fact, he doesn't even ask convergence. This is up to subsequence, and this is why the theory is so deep. If by some subsequence that r goes to 0, this blow up converges to a function of the form 1/2 of a specific vector x squared, I call it regular. If it doesn't converge, which means that it's impossible to find a subsequence for which this converges, Caprali says that the pre-boundary point is not regular or singular. Okay, and the key point here is because Caprali is not saying that, okay, because it'll be very hard to prove that this converges to all points. It's a full sequence that converges when r goes to 0. That's a very rigid condition. What he says is that up to a subsequence it converges to a function of that form. He doesn't even ask E to be the same for all subsequences. None of them. And this is part of the theory that he develops to prove that, assuming that there exists a subsequence that converges to one of them, then this vector E is well defined, and as a matter of fact, the whole sequence is going to converge to that specific global configuration. Anyway, So the Caprali free boundary theory goes as follows. The free boundary is in fact a smooth surface. It's a C1 alpha surface, and therefore reanalytic afterwards around any regular point. Okay, and again, the theory that Caprali developed in the late 70s is so profound because his definition of regular point is very weak. He also shows that if you are in a singular free boundary point, then there exists a modulus of continuity, universal modulus of continuity omega, such that the free boundary is trapped by like a strip that goes to 0 as r goes to in the velocity omega r. So you see how powerful this is, because if for some r, if there exists a one small r, so that the free boundary cannot be placed in any strip of that width, then automatically the point becomes a free boundary, regular free boundary point, and the free boundary becomes smooth automatically. So that's why it's a very powerful free boundary regularity theory. Okay, so once you understand this, it's important, this comes from a further development of free boundary theory, is that while the free boundary may indeed develop cusps, and this is something that Caprali has already observed, is that free boundary points for the obstacle problem, solutions may develop cusps, the free boundary may develop cusps at those surfaces. It has been observed later on by Eisen and much earlier by Pigali and Serra that solutions behave, for some miracle, behave smoother at those points. Okay, so if you are in a singular point, the free boundary behaves bad, but the solution itself moves in a slightly smoother fashion than just C11. Again, this has to do with monotonicity formulas and classification blow-ups using monotonicity formula. So the analogy that I'm trying to convey to you today is the following. If the obstacle problem, you have regular free boundary points, then what one should expect is for the degenerate PDEs of that form should correspond to the case when f is of order 1. In other words, f is away from 0. Okay, and I hope you can see the analogies, because the regular free boundary points are the ones that when you zoom in, you have up to some subsequence, you have like a rigid configuration. This should be saying that this forcing term is away from 0. Whereas singular free boundary points should correspond to f vanishing. Okay, so once you understand this analogy and you assume this analogy, you should try to prove the corresponding results. Okay, and if you understand this analogy, the corresponding results should be more or less easy to conjecture. So the first one is this theorem that says that if you have weak solutions of this problem, okay, and then if in fact the infimum of the absolute value of f is bounded away from 0, then the lim sup of u of x minus u of x naught divided by x minus x naught to the power p prime is bounded away from 0 as well. Okay, and this, you see that this is a very geometric, it's a very geometric estimate, because what I'm telling you is that you will achieve a critical point at least with a particular velocity, right? Not at least, at most with a particular velocity. So in particular, this is very easy to confirm, is that in particular, if you fix a critical point, remember that at the critical point, the gradient is 0. So you have the Taylor expansion with the gradient being 0 on the bottom of, on the top of this estimate. What I'm saying is that because of this estimate, solutions can never be better than CP prime smooth at any critical point. For all other points, solutions are as smooth as the forcing term allows. If F is reanalytic, then solution is going to be reanalytic away from the free boundary. But when it reaches the free boundary, then solutions are no better than CP prime. Okay, so this is, it's kind of a counterpart of the CP prime regularity conjecture. Okay, so the geometry of the problem is this: you have a critical point. So, and as a matter of fact, this kind of guides us to the proof, what I'm going to explain in a second. Basically, what we're proving is that there is these barriers that one can build up, and you trap the solution between these barriers. And basically, what I'm saying is that if F, this forcing term, is away from 0, then because it's, you see, because it has to be above this barrier, it can never reach the critical point, is smoother than CP prime, right? Again, this is a simple argument using the Taylor expansion of U at a critical point, keeping in mind that at a critical point, the gradient is 0. So therefore, in the Taylor expansion, the first order term is 0. So it doesn't show up. So basically, what you're saying is that U grows away from X naught in a CP prime fashion. Okay. So of course, I'm not going to give you the technical details of the proof, but I'd like to comment that in fact, this theorem should be thought as a non-degeneracy estimate. Okay, and this is a typical result in free boundary theory. And it follows very closely standard arguments in the theory. That's basically how we prove non-degenerate estimates in cavity problems or in obstacle problems or in many other kind of free boundary problems where you have some sort of estimate, geometric estimate to be proven of that sort. Okay, and the proof, as a matter of fact, what you do is that you use barriers that has to do with x to the power p prime, and you short up the solution. For point by point, you build up that barrier like shorting up. You make those steps and you kind of construct this barrier point by point, and you glue them together. And at every point, you're going to have this barrier not allowing you to go faster than CP prime to 0 or to the critical point. Okay, so now let me make the problem slightly more complicated for practical purposes. Now, instead of looking at the p-laplacian itself, I'm going to look for a more general, and I have a reason for that. I'm going to look for a more general equation with coefficients. Okay, so we know from the very beginning, for the early stage of the theory, that the regularity of the coefficients have a deep impact on the regularity estimates for the solution itself, right? So in fact, if you are studying just like, let's say, the aharmonic functions, and A is kind of a p-laplacian. Think of, if you like, think of the p-laplacian adding some coefficients, okay, which takes into account the roughness of the medium. Okay, so there are two kind of results. There are degenerate type of estimates, which says that if you don't assume any smoothness whatsoever on the regularity of the coefficients, then solutions are Hilbert-continuous. And this is a very important result, even though you're very far away from what you want it to be, but this gives you compactness of solutions, okay? So this is a very important result. And there are the perturbative theory, where you assume that the coefficients are continuous, so it moves continuously point by point. Then solutions are C1, C01 minus. So solutions are C0 alpha for every alpha less than 1, but it may fail to be C1, C01. It may fail to be Lipschitz. Okay, and there is also the corresponding Schauder theory. In other words, if you assume slightly more on the smoothness of the coefficients, if you assume that the smoothness are, let's say, C0 alpha, Hilder continuous, then solutions change their regime and become C1 beta. And this beta, of course, depends on the dimension, depends on P, and also depends on alpha. The hardest borderline case is when you assume just enough continuity on the coefficients. You assume that the coefficients are Dini continuous. The solutions are C1, they are differentiable, but they may fail to be C1 epsilon for every epsilon. So you are in this borderline case where solutions are just differentiable, but not more than that. Okay. Okay, so now let me show you the counterpart of regularity estimates for free boundary problems at singular, or the analogy of the singular points. So the theorem goes as follows. If you assume that you have a weak solution of a problem of that sort, and then I'm going to assume, that A is just Dini continuous, and it behaves like the p-laplacian. And I'm going to assume that F vanishes at a specific point with a specific rate, right? So I'm saying that U vanishes as a power of the gradient to some power m. Then at any critical, interior critical point, you have slightly more regularity. Solutions become C1, 1 over P minus M plus 1. Okay, and I will explain this in a second. So you gain smoothness at that critical point. Okay, so the main idea, this is a much more delicate theorem to be proven. So the main idea, and remember, you have to keep in mind that you are in a system with just Dini continuous coefficients. So the fact that you can prove C1 alpha estimates is already very remarkable. Okay, you shouldn't be expecting to prove C1 alpha estimates because the medium is just Dini continuous. Okay, and this is even remarkable in the uniform elliptic case, where critical points are not troublemakers, right? But anyway, this is something that we had already observed, that this happens. You can go from C1 to C1 epsilon naught for some very small epsilon naught, and this is a very like the starting regularity estimate. So we jump from C1, that comes from the general theory, so you're not using any geometric information of the solution, and you go from C1 to C1 epsilon at a critical point. Okay, and again, this is something that had already been observed a few years ago. And then we have a key improvement of regularity. We prove that once the solution becomes C1 epsilon, then it becomes C1 epsilon plus a little bit. Okay, and this little bit has to do with this epsilon initial. So you're gonna have a very nonlinear iterative process going on, because for every, now we try to build up the whole system again and apply the key improvement lemma over and over, right? But every time that you do so, the extra bit of regularity that you get depends on the previous one. So this is a very highly nonlinear recursive iteration that gives you this sort of estimates. C1 gamma of n implies C1 gamma sub n plus a delta sub n, and this delta sub n depends on many things, including the previous estimate that you had. Okay, so after you have that, you have a very interesting problem, which is kind of an analysis problem. It's a nonlinear recursive equation that you need to find the limit. Okay, so this is, I remember taking an analysis, introduction to analysis course by, of course, in Brazil, in Fortaleza, with my professor Fabio Montenegro, and he used to give us problems from the famous Alon's book on this kind of things, that you have to find the limit of nonlinear recursive formula. It paid off several years later to be able to calculate this kind of thing. It's a beautiful argument, but it's kind of a simple but rather interesting argument to prove that this thing does converge and converges precisely to that number. Everything fits almost like magic. So final remarks is that existence of uniqueness solutions is a huge business, very beautiful theory. That there are many people working on these kind of solutions, and it's very interesting to notice that the conditions that they have to show existence of uniqueness, a weak solution of these kind of problems, it has to do with the estimates that we prove. Okay. And many people have worked on these kind of problems. The second remark, and I'm going towards the concluding my talk today, is it's alluding to realize that these new estimates are a sort of improved CP problem in the following sense. And this is what I was trying to say when I said that you have an equation of the form 0 equals 0 in an abstract sense. Is that when you are in a critical point, the diffusion vanishes, but so does the forcing term. So they kind of adjust themselves in some sort of, one compensates the other, and that's where you get this extra piece of information. Of course, there is a magic happening because you are getting these kind of estimates regardless of the continuity of the coefficient, which is remarkable. But this is the technical part of the proof. So if you compute this number, you will see that this number, this is just an algebraic manipulation. This is sort of p minus m prime. So somehow, and it goes well with the analogy, that somehow having a forcing term that vanishes in the rate m kind of reset the p. So you bring p minus m, which is going to be slightly below p, and therefore the prime is going to be bigger than p prime. Okay, remember that the conjugate reverses the order. Okay, now the final thing that I'm going to mention in a minute that I have is that the theory is not really limited to the maximum regularity for the constant coefficient equation. So if you think that solutions of that equation has a maximal C1 alpha regularity at the critical point, then everything is bounded by this alpha max, and there is no other way to go around that, because 0 fits the conditions of our theorem for any m. So of course anything that I prove has to be restricted to this best alpha. But the question is whether can I break free from such a theoretical barrier, and in fact this is true at critical extrema. So if you have this kind of problem and x is just continuous then at any interior critical point you have solutions are 1 over p minus m plus 1. Okay, so you see that it's an interesting fact that if you are in a local maximum or a local minimum, then I can even go beyond C1, C2, C3, C4, can get a much bigger, much higher regularity estimate. And that's also, I find it very remarkable because somehow you go about the optimal regularity for the constant coefficient homogeneous problem. Okay, and with that, I thank you for your attention, and I think this is a good place for me to stop.
Thank you, Professor Eduardo Teixeira, for this very nice talk. Let me see if we have some any question or comment from the audience. Not from the moment, but I have one, if you allow me. Not rather technical, but you mentioned that some conjectures and interesting results along your lecture. Yeah, regarding the up-to-date state of the art of the subject, how far from a proof of those conjectures do you think the researchers on regularity of PDEs are?
Okay, so this is a tough question to answer. I know that this is a very active. It's like everybody working seriously on this kind of problems. This is like one of the important problems that certainly would give a lot of attention. And I know many people that are interested in these kind of problems. The current technology is not going to do it for you. Okay? So it's impossible to kind of revise no estimates. I would expect that it's hard to prove those estimates just with the usual techniques available in the market. I personally, and of course, I'm biased to say that I'm personally very keen to think that this analogy from free boundary theory can shed some light. I'm not saying that it's going to solve the problem, but I'm very optimistic that it sheds some light. And the reason why I think so is because in free boundary problems, if I tell you that the solution of the obstacle problem is C1 alpha, which you come for free, solutions to the obstacle problem are C1 alpha, comes basically for free. It's an elliptic estimate. It's straightforward. But if you're not able to prove C11, which is the sharp optimal estimate, you cannot evolve the theory. So the whole theory of free boundaries is devoted to prove geometric alternatives for regularity. And it's a very robust theory that has its roots on seminal ideas. And I think that one needs to be able to import those insights to these kind of problems. And once this is my best guess, I would say, is that I'm not saying that it's going to be able to solve the problem because it's a very difficult problem, but it's a good idea, I would say.
Nice, thank you. Let me see if you have some manifestation from the audience. If we don't have, I would like to thank you so very much again, Professor Eduardo Teixeira. It is in fact a great pleasure to have you in our workshop. Thank you so much.
Bye.
Bye bye. We will resume in 10 minutes with our next and last talk in this afternoon section. Please keep going with us. Bye.
Good afternoon for all. I am Francisco de Paiva. I am professor at Department of Mathematics of Federal University of São Carlos. Now we will resume our workshop. Sorry by the delay. It's a pleasure to me, very pleasure to me, to present Professor João Marcos do from Universidade Federal da Paraíba. Professor João Marcos is a distinguished researcher in the area of elliptic equations and with many contributions in the Turner-Gamose type problems. He will talk about Turner-Gamose type inequality in weighted space. Welcome, Professor João Marcos.
Okay.
For being here with us.
I'm glad to be here to talk about our work, and it's a great pleasure to share with you new results on Turner-Gamose inequality in the weight space.
Thank you, Professor. You can begin. Thank you.
Okay, so as I said, today I will talk about new results on Turner-Gamose type inequality in weight space. These results are in collaboration with José Francisco de Oliveira from Federal University of Piauí. Okay. Let me say some words about the abstract of the talk. We consider Turner-Gamose inequality associated with the embedding a class of weights over level space into ortho space. And our main goal is to present recent result on the existence and non-existence of extremal functions for sharp Turner-Gamose inequality on Adimur-Drouet type for fractional dimension on entire space. Okay, let's begin from the beginning, at the very beginning. Okay, I want to recall the definition of sublevel space, which is related with our main topic of my talk. We consider a bounded domain in Rn, and we consider the sublevel space we can see as a closure of the compact support smooth functions with respect to the Dirichlet norm. So this is the space, and we know the classical sublevel embedding that in the case that P is strict less than N, we know that the sublevel space is continuous embedded in Layback space for any Q strict less than P star, where P star is the critical sublevel exponent given by this expression here. In the limit sublevel case, when P equal to the dimension of the space, P equal to N, we know that the sublevel space is embedded in all Layback space LQ for Q is strict less than L infinity. Formally, the sublevel exponent goes to infinity if P goes to N. And as you already said, that our sublevel space is embedded in all Layback space LQ. However, it is not embedded in L infinite, as you can see with this simple example. So if you consider this function, we can do an easy calculation and see that although this function belongs to the sublevel space, this function does not belong to L infinity. So at this point comes a natural question. What is the maximal growth of the function f, such that if u belongs to the sublevel space W1 and 0, we have the integral of fu is finite. So we know already from the classical sublevel embedding that this is true for any polynomial function. But we want more, no? And then this question was answered by 4 mathematicians: Udovich, Korolev, Pietri, and Trudiger. Independently, they proved that the maximum growth is of exponential type. It is in some sense natural, because we know that any polynomial can be considered. So in the next step, it will be exponential. The sum of polynomial when n goes to infinity. Okay. So they prove, they changed the target space. Instead of considering Layback space, they consider Orlick space. And they prove that the Sobolev space is embedded in L phi, where L phi is a Layback, is a Orlick space associated to this any function here, phi given by this expression e to the power m times t to the power n over n minus 1 minus 1. So this is the answer given by Udovich, Korolev, Pietri, and Trudiger for this embedding. Okay. Let's emphasize that they prove that this, indeed, we have a continuous embedding if this coefficient mu is sufficiently small. And it also comes easily another question. This exponent, n over n minus 1, is optimal. And this was proved by Hempel, Morse, and Trudiger, that indeed this exponent is optimal. So the Hempel, Morse, and Trudiger, they prove that if you have another n function in another Orlick space associated, L psi, when we have this L psi here, when the power is greater than n over n minus 1, we can see that we do not have the embedding. We do not have the embedding of our Sobolev space into the Orlick space L psi. So in this sense, the exponent n over n minus 1 is optimal. Okay, and later on, Moser gave a very nice improvement of this Udovich, Korolev, Pietri, Trudiger inequality. Moser proved the following. Indeed, Moser have a problem in geometry, and he need to find the best beta. And he proved that the best beta is given by this expression. It is related with the surface of the area of the unit sphere. In the case of the plane, the best exponent, or the Moser exponent, is given by 4 pi. Okay, so Moser also proved that if beta is greater than beta n, although this integral is finite, we can make this integral arbitrarily large by the appropriate choice of the sequence. Okay, later on, Lyons proved that we can go beyond 4 pi. You can, if you, in this sense, you have a sequence. You have a sequence normalized in the Sobolev space. It converges weakly to U. Then this limit sup is finite if P is strictly less than this number, beta n over 1 minus the norm of the gradient, the Dirichlet norm. You can see here that if U is non-trivial, this number is strictly bigger than beta n. So you can go beyond this, the Moser exponent. Also, I have to mention that later, Cern, Chianchi, and Henkel, in 2013, they found a mistake in the proof of Lyon's and complete the proof. Okay, so Adimot and Drouet, to complete the analysis of Lyon's, they proposed the following version, and each was generalized by Young later for dimension greater than 3. Adimot Drouet, he proved for the case n equal to 2, and Young for dimension greater or equal than 2, and proved the following result. This supremo is finite if alpha is 3 less than the first eigenvalue, and is infinite if alpha is greater or equal than lambda 1, the first eigenvalue. You see that this, in the power here to the exponential, we have beta n, which is the Moser exponent, times 1 plus alpha and the norm of u. So you can go a little bit farther, the Moser exponent. And this lambda 1 is the first eigenvalue, as we have this variational here. Okay, so the next chapter of this class of problem is the existence of extremal function for true Moser inequality. It's a very important point. And here I have to mention that differently from the classical Sobolev case, it was proved by Carlson Chang that the supremo is achieved. We know that for the classical Sobolev case, the supremo is only achieved when the domain is the entire Euclidean space. But Carlson Chang, they proved that for any ball in Rn, this supremo is attained. Okay, Struve in 1982, he proved also that the supremo in the Schrödinger-Moser inequality is achieved if alpha is less than alpha n. Alpha n is the Moser exponent. But you see, the Struve result is for small perturbations of ball. Let me recall that the proof of Carlson Chang was just for the case of ball, and this Struve proved for a small perturbation of balls. Later, Fleury proved that in any bounded domain in R2, this supremo is achieved. Finally, in 90, Lin proved that is achieved in any bounded domain of Rn. So Lin proved the complete result. We, in collaboration with Figueiredo and Wolff, we give a new proof for the Carlson-Chang result. And for that, we use the concentration compactness. We should mention that in the paper of Lyon's and the paper of Carlson-Chang is almost the same time. They publish almost the same time. So Carlson and Chang didn't know about the argument of Lyon's. And we use the idea of Lyon's to give a new proof for Carlson-Chang result. And Young not only proved the supremo is finite, but also he proved in this paper this supremo is achieved. Okay, let me begin to say some words about the Schrödinger-Moser inequality for weight space, weight Sobolev space. At this point, it's very important to to recall the Moser result. Moser proved that this supremo is finite when you have this condition. The mu is less or equal than the Moser exponent and is infinite otherwise. Okay, so to prove this result, Moser used symmetrization. He used a completely different proof from the result of Porojev and Trudiger. Porojev and Trudiger, they start the series associated to the exponential and got estimates for the norm of the function. And he proved that for a small value of mu, he can control the series and prove that indeed the series is convergent. But Moser gave a different proof. The first point interesting in the argument of Moser is that he proved that, okay, we can reduce our problem for the radial case if we use Schwarz symmetrization. And you consider a ball with the same volume of the domain omega, and he reduced the problem for the radial one. And after that, he used some change of variable and transformed the problem in one-dimension problem. One-dimension problem. It is to start this supreme in this space. No, this is the idea of Moser. And we use this idea of Moser to consider a more general class of Trudiger-Moser inequality for the weight Sobolev space. So this is I'm just explain using that the function is radial, we can reduce to this situation, and then and here we have let me introduce the weight Layback space. This class of space was already studied by Kuffner and Opik in a classical book on hard inequality. They consider the Layback space, the measurable function, such that this integral is finite. And associated to this, we consider the weight Sobolev space is the function that are locally absolute continuous functions in the interval 0, r, such that the limit is 0 when r goes to big R, and the function belongs to Layback space LP theta, and the derivative of u belongs to LP alpha. And with this norm, this space, the Sobolev space is a Banach space. Remember that the weight comes here in the integral, in the r to the power theta. Okay, so here we distinguish two cases. This I have to mention that the motivation to start this class of problem comes from a paper from Clement, Mitidieri, and Dijari de Figueiredo. Some years ago, Mitidieri gave a talk at Unicamp, and he present some results of Bressis-Dierenberg type results for a class of operator more general than the p-laplacian, in the natural space for the variational framework to start that class of problems is exactly this weight Sobolev space. And in that occasion, they considered just this case, the Sobolev case. It corresponds to alpha minus p plus 1 greater than 0. And the true degenerate case corresponds to alpha minus p plus 1 equal to 0. In the classical case, each corresponds to p equal to the dimension, the true degenerate case. Okay, so as I already said, this book, Opic, Kuffner, Hard Type Inequality. This is a classical book. And in this book, you can find the Sobolev embedding for this class of Sobolev, weight Sobolev space. The weight Sobolev space is embedded in the Layback space if this Q is in the interval between 1 and P star. Right? P star is this, say, this Sobolev exponent for this class of Sobolev space. Okay, so, but in the two degenerate case, our weight Sobolev space is embedded in all Layback space. But as in the classical case, is not embedded in L infinity. And you just can use this simple example as before, the same one. So in collaboration with Zé Francisco de Oliveira, in 2014, we introduced a new class of true degenerate inequality for this class of weight Sobolev space. Now we consider this notation, and we prove this theorem. First, for any function in the Sobolev space, the exponential belongs to L1. And this supremo is finite if mu is less or equal than the Moser exponent, and is infinite if mu is greater than the Moser exponent. And moreover, this is not 27, it's 19. The supremo in 19 is attained if mu is less or equal than the Moser exponent. This was proved in this paper here. Okay, you can rewrite in this way. The supremo is finite if mu is less than the Moser exponent, and is infinite otherwise. And then in here, the Moser exponent is given by this expression here. Okay. And later on, also in collaboration with Zé Francisco de Oliveira, we prove a result of Adimur-Drouet type, Adimur-Drouet inequality, for the case when R is finite. Until now, we are discussing just the case that we are in balls. So in this case, we can prove that the supremo is finite if eta is strictly less than the first eigenvalue associated to this space. Okay. Now we have a new chapter. We discuss now the true degenerate inequality for unbounded domain. Okay. And then for unbounded domain, the first result that we know, it was proved by Cal in 92. Cal wants to start this problem in whole R2 under this condition, and he wants to consider the exponential case. So his idea was to use the mountain pass lemma and use an argument similar to the classical paper from Brazil's Layback to get a critical point for the associated energy functional given by this expression. Okay, so, but here he you have to face some difficulties. First, the embedding of the classical sublime space into Layback space is not compact. Also, this set also is not compact. This is sphere, the ball, indeed. It's not compact in the Auric space. So to overcome this difficulty, you have to use the concentration compactness of Lyons. And also, you have to introduce a kind of Trude-Gemose inequality. And this is exactly as is in his paper. No, it's similar to Mose. He said, no, we have a following embedding length. If you are in U belongs to H1, the Dirichlet norm is far from 1. The L2 norm is bounded by M, so the supremo is bounded by a constant. It depends of the small m and capital letter M. But it is a uniform constant, independent of U. And this is the first time that it comes this class of Trude-Gemose inequality for unbounded domain. Later on, we generalize the result of Cal for the space W1 1n in all Rn. We want to start this problem, and we consider the appropriated space, taking account the potential V, no? And under this condition, we have to introduce a new class of Trude-Gemose inequality. But now I have to come back a little bit to recall that for this case, Cal consider the exponential minus 1. But in the general case, we have to consider the exponential minus the first term of the series of the exponential. Because this term does not make sense, because you know that our space W1n is embedded in R for R greater or equal than n. So you have to subtract the beginning of the series. This is what we did. Okay, and we proved that this supremo is finite, and it depends of these values. So now we are with alpha strict less than the Sobolev exponent. I have to mention that our result is different from the Cal result, but indeed they are equivalent, as was proved recently. Okay. Let's consider the truncated exponential function. We just consider we consider exponential minus the first terms, and with this, in collaboration with José Francisco de Oliveira, we prove this class of Trude-Gemose inequality we call the scaling invariant form. This is this integral is, we have this inequality, it is scaling invariant. And if mu is greater than the Mose exponent, the supremo, this inequality 26 does not hold. Okay. And here we have a version of the scaling invariant Trude-Gemose inequality for the case that R is finite. Here, this one, this one is the case when R is infinite. This is the first result that we have for the Trüdingen-Moser inequality for this class of weight sublevel space in the whole space. In this, what I mean that is our domain is unbounded domain. And here is a version for a bounded domain. We have this belongs to L1. This supremo is finite if the coefficient mu is less or equal than the Moser exponent, and infinite otherwise. And moreover, 27 is attained for all mu positive and less or equal than the Moser exponent. Okay. And also here, we have this Trüdingen-Moser constant. Now, again, as I said, we are in the case where unbounded case, unbounded domain. This supremo here, is finite. And also we obtain this relation between this constant, this Trüdingen-Moser constant, this supremo. In the case, always in the case that the coefficient is straight less than the Moser coefficient. And also we have this relation between the Trüdingen-Moser constant and the Trüdingen-Moser scale invariant constant. This class of result is very important to prove our main result about the attainability of this supremo in the case of unbounded domain. So for that, we need a result of Lyon's type for entire space in the case of R equal to infinity, unbounded domain. So consider a sequence in our weight sublevel space. Here, I emphasize that our domain is unbounded, normalized, weakly convergent, and non-trivial. So this limit super is finite if Q is strictly less than P, where P is given by this expression. And this is a type of result that we can go beyond the Moser exponent. Okay. And moreover, we can find a sequence normalized such that the supreme becomes infinite if Q is greater or equal than P. Okay. With this result in range, we can prove a multi-Drouet result for the entire space. We just use that estimate in this elementary inequality. And then we have the supreme becomes finite. And we state here. This multi-Drouet constant, the supremo, is finite if mu is less or equal than this coefficient, and eta is less than 1. And infinite if mu equal to the Moser exponent and eta equal to 1. I want to emphasize that this result, this theorem 3, improved the recent result from Abreu and Fernandes, because there, in their case, eta is equal to 0. So we consider the result more general than their result. And also we have this subcritical case. Now this in this case, again, we improve the result of Abreu and Fernandes. If under this condition, this Adimur-Drouet, this is the first result about the attainability. This Supremo, the Adimur-Drouet Supremo, is attained. Under this condition, we have a function in our weight Sobolev space that attain the Supremo under this technical condition. And also, we prove that in the critical case, we also prove the attainability. And finally, we have a non-existence result. It is there exists some mu0 such that the Adimur-Drouet constant is not attained under this condition, either strict less than 1 and mu strict less than mu is a result of non-existence. Okay, so let me say some words about this. Is the Abreu Fernandes paper published in 2020 that we improved some results. The Adimur-Drouet paper, very important paper, where we introduce a new class of two-dimensional inequality. The Cow paper, the first one where we have the two-dimensional inequality in the unbounded domain. The Carlson-Chang paper, where we have the first result about the existence of Stremal for two-dimensional inequality. And the Cern-Henkel paper that they complete the proof of Lyons. The paper of Clément, de Figueiredo, and Mitidieri, where they start the Brzezinski problem for this class of weight Sobolev space. This is the paper where, in collaboration with de Figueiredo and Ruf, we prove the attainability of two-dimensional inequality. We give a new proof for the Carlson-Chang result, and this is the paper from Zé Francisco, where we prove for the first time the two-dimensional inequality for a weight Sobolev space. I think that this is all we have for today. Thank you.
Thank you, Professor João, for the very nice talk. And now I want to see if you have some questions. Please, if you have some question, write down here. But João, I want to know about what kind of problems do you solve? What the equation or what you solve? It's a version of a radial version of some equation, or it's just a radial problem.
Yeah. As I said, the motivation to study this class of problems comes from a talk from Mitidieri at Unica. And the paper of Clément, de Figueiredo, and Mitidieri, they start the Brzezinski problem for this class of radial operator. Is a class of operator that includes, in particular, the Laplacian, the p-laplacian, and a radial version of the K-Hessian operator. And in that talk, I realized that they didn't consider the the two-dimensional case. So I said, okay, but they didn't consider the two-dimensional case. We can do it. Let's try to do it. And so the first point we have to do is to introduce a new class of two-dimensional inequality. And to start the the problem involving the K-Hessian operator, the radial case, involving critical growth, the first step is to introduce a new class of embedding.
Okay.
And in this paper with Francisco, we did that.
We are just in this stage of the problem. João, thank you so much again. I think that you don't have more questions. Also, oh no, okay. I would like to thank you again, and also the audience, and also the audience. I just want us to remember all of you that tomorrow we will start again at 9 a.m. local time, São Carlos, São Paulo, and we will start with. We will resume with Professor Manuel Del Pino, and after, in the sequence, Professors Andrei Zuckin, Augusto Ponce, Giovanni de Figueiredo, and Marcos Pimenta. And thank you all for the presence in the workshop, and you will be here tomorrow, and we hope you will be joining us also tomorrow. Thank you. Bye.